Hello, we're Team PULMAtech, and we're working with Edwards Lifesciences on the Alternative Access TAVR Improvement Project. I'm Francis Sung, the project lead. My fellow PULMAtech members are Lance Losorelli, our design lead, Gabriella Anderson, our data manager, Robert Pell, our coordinator, and Joshua Mantock, our quality control. Our mentors are Ilan Tamir and Jeffery Kasalko, both directors of R&D at Edwards Lifesciences. I will now hand it off to Lance to talk about our background.
Thank you, Francis. I'll now be talking about our background, which is the TAVR alternative access procedure. TAVR, or transcatheter aortic valve replacement, is the standard of care for treating aortic stenosis, a condition in which the aortic valve in your heart becomes stiffened over time, which leads to decreased cardiac output and eventual heart failure. TAVR is a minimally invasive procedure which replaces the diseased aortic valve with a prosthetic one via a catheter system. TAVR is generally performed via transfemoral access, in which the system enters a small incision through the femoral artery. However, in 10% of cases, transfemoral access for patients may be fatal. This is due to high tortuosity, which means drastic bends and angles, or high levels of calcium buildup. Both of these increase the possibility of trauma during the procedure. In this case, physicians may use what is known as alternative access, in which alternative access points are used instead of transfemoral access. In this case, the most common are transcarotid or transsubclavian access. So what are the problems and needs associated with TAVR alternative access? The problems stem from the introducer sheath, a vital component to the TAVR system, which creates a protective barrier through the artery wall for the catheter tools to enter and traverse safely. Furthermore, the sheath has a specialized tip to prevent damage during entry. Unfortunately, the sheath must be inserted completely to ensure security and stability, but this cannot be done during alternative access. This is because the sheath is designed specifically for transfemoral access and has a length of 37 centimeters. But the various alternative access approaches require various different lengths for TAVR. For example, the transcarotid approach requires 20 centimeters, while the transsubclavian approach requires only 17 centimeters, both of which are drastically shorter than the introducer sheath length. Which brings us to our problem. The introducer sheath must stick far out of the body during alternative access procedures to ensure proper valve placement. Furthermore, one physician must have the sole job of manually holding the sheath in place to avoid over-penetrating the heart. This is not only wildly inefficient, but is also unstable and unreliable, which greatly increases the risk of valve misplacement and trauma during the procedure. Therefore, there is a clinical need for a way to adapt the introducer sheath system to alternative access TAVR procedures. I will now be handing it off to Josh to talk about our market strategy.
Thank you, Lance. Now I will be talking about market strategy. Our device would be used by cath lab technicians in TAVR hospitals. We want to make sure our product is easy to assemble and use. The current market size for TAVR procedures is listed at $5.25 billion in the year 2021, and the projected market value is set to increase to about $12 billion by 2028. Our business model involves creating a low-cost device sold within the original Edwards packaging. We ultimately agreed on this model because it would be cheaper to package the device. By packaging our part components with Edwards' original packaging, the operators can decide if our parts are needed for alternative access. Our primary competitors are Medtronic, LivaNova, and CryoLife. These companies have their own devices, the purpose for TAVR procedures, but none have any products currently on the market addressing alternative access. I will be passing it on to Francis to talk about design principles.
Thank you, Joshua. I will now talk about our design principles. Our device, the DuoLink, enables clinicians to adjust the sheath length to match the patient's vasculature at various access points while maintaining the original tip geometry. This device preserves the benefits of the original E-sheath while addressing the shorter length required of alternative access. To implement our device, a clinician first cuts the sheath flush with the hub. The device is then snap-fitted onto the hub. The clinician then slides the sheath onto the DuoLink expandable tip. Finally, the compression nut is tightened to secure the sheath. We also came up with an alternative solution focusing on supporting the sheath. The sheath support device would allow clinicians to operate the e-sheath without having to use extra hands, freeing them up for other important tasks. The e-sheath will be secured with a snap fit after insertion into the body. The orientation will be locked once into position to prevent damage to the vasculature. This will ensure that the e-sheath is at the right depth to prevent puncture of vessel walls while remaining concentric with the artery. The base frame of the device will be supported with the way of the patient by the way of the patient. I will now pass it on to Gabriella.
Thank you, Francis. I will now be talking about our evaluation criteria. Our evaluation criteria is made up of both our design and acceptance criteria. For our design criteria, we focused on 5 modes in regards to sheath modification. These include the ease and complexity of assembly, the ability to decide sheath length, and maintaining sheath integrity and sterility. Our acceptance criteria consist of a maximum 5-minute assembly time, a 10 Newton maximum assembly force, a 3 mm tolerance for the desired sheath length, the ability to survive at least one full rotation with 25 pounds of shear stress, and the ability to withstand a minimum of 258 millimeters mercury of pressure. I will now pass it on to Robert to talk about validation and verification.
All right, thank you, Gabby. So I'll be going over validation and verification. So for our first test, we would have the hemostatic pressure chamber. We would take a saline solution at 129 millimeters of mercury and increase the pressure so that it would go up to about 258 millimeters of mercury to test if there would be any blood leakage. In this first test, we would pass at the sheath connection joint, but actually fail at the E-sheath hub connection. So you can see the leakage on screen. And then for a second test, we would have a robotic arm rotate our device with a 25-pound shear weight connected to it, and it would have to pass at least one rotation to be considered safe for use. In this test, we would pass with 14 rotations before rupture and ultimately fail around 24 rotations. And in our final test, we would have anatomical modeling, where we had a cath lab clinician assemble and test our device on a silicone model with flesh and vasculature, and they would say that it passes with some difficulty, but they gave us feedback to ensure consistency of our device assembly and operation. Then we had a second round of trials where we did the same exact tests. So for the hemostatic pressure chamber, we initially had two leakages with the initial testing, but we would modify it with Teflon tape, and we would actually pass at the thread again and make less leakage so it was less than 10 milliliters per hour and pass the Edwards criteria to be a useful device. Then we had the flexure tests, where we tried to make it more consistent and remove dexterity in assembly, but this would actually backfire and cause our device to fail after one rotation. Next, we'd have anatomical modeling, where we had our mentor assemble the device and test if it would be easy to assemble after our modifications, and they said that they had some assembly difficulties still, but it would still pass as a device and could be streamlined and more foolproof. So then for our future directions, we want to continue improving our dual link and make it a minimal viable product, and continue to explore our sheath support solution. But we do have some feedback that it's simple and easy to do, but we just got to fix that ability with the dexterity in the assembly. So now, thank you, and here are our references.